All right, guys. So in Unit 5, we're going to start by talking about what are called discrete random variables. It's actually going to turn out that a lot of the work that we did in both Unit 3 with the normal distribution and in Unit 4 with our rules of probability is all kind of led up to this section, which is what are called probability models. We're using a lot of the stuff from the last two units in this unit as well. We're going to start off with a few definitions just to make sure that we're on the same page. I'll give you some examples of that, and then we'll run through some examples of kind of how all this stuff works. So to begin with, we're going to start by talking about what are called random variables. So what is a random variable? It's a random event with numerical outcomes. So an example of this would be rolling dice. It would be an easy way to think about this because obviously when you roll a dice, you get a number between 1 and 6. That's a numerical outcome. We're not talking about drawing names out of a hat or picking colored marbles out of a bag. Those are not numerical outcomes. When you pull a marble out of a bag, you get red or green or blue. That's not a number. So a random variable has to have a numerical outcome. There's going to be two different types. The first of which we're going to talk more about today is a discrete random variable. The second we'll talk more about in the second video, which is going to be what's called a continuous random variable. So in a discrete, what makes those different? Let's talk about that. A discrete random variable is where all of the possible outcomes can be listed. So an example of this would be rolling a dice. If you think about it, you can list off every single thing that's in the sample set. You're going to roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So it's possible to list out every single outcome. A continuous random variable, that's not going to be the case. All possible outcomes cannot be listed. So this is an example where maybe you're looking for the average height for, let's say, students at North. Now, while we could theoretically list all of those, it wouldn't make much sense to sit there and list off every single height for every single student. There's just not going to be enough that are the same. And even if, let's say, I'm 5'10", I might be a slightly different height from someone else who's also considered to be 5'10". You know, it might be that I'm a little over 5'10", maybe they're a little bit more over 5'10". You know, you can get a little bit more exact. So a continuous random variable, you're not going to be able to list off every single outcome that's possible. Finally, a probability model is the collection of all possible values and their probabilities. So a probability model is usually best thought of as dealing with discrete random variables. So let's in fact continue with that rolling the dice example. We would list off all the possible outcomes, so 1 through 6, and then we would list the probabilities of each of those happening. So probably rolling a 1 is 1 out of 6, rolling a 2 is 1 out of 6. In fact, if you think about it, rolling any number, the probability for each of those would be 1 out of 6. So your probability model would look something like that. So let's see an example of kind of how all this works. So imagine that you're selecting a U.S. high school student at random. We're going to define the random variable X, capital X, to be the number of languages spoken by that randomly selected student. The table below gives the probability distribution of X based on a sample of students from the U.S. Census at School database. So languages, anywhere from 1 to 5, and probabilities are listed there for us in that probability model. Let's first show that the probability distribution for X is legitimate. So remember, when we're trying to show that a probability model is legitimate, we're essentially doing what we did last unit. There's basically two things we need to check. We need to check that all of the probabilities are between 0 and 1. We also need to check that the sum of all of those probabilities, the probability of our sample space, adds up to be 1. The first one should be pretty easy to check. 0.63, 0.29, 0.06, and so on. Those are all in fact between 0 and 1, so we are good there. The only thing we have left to check is to see if they all add up to be 1. And in fact, they do add up to be 1 if you put those into your calculator and add them all together. So yes, this is in fact a legitimate probability model. Next, it wants us to make a histogram of the probability distribution and to describe what we see. Okay, so making our histogram, we'll go ahead and draw it like so. We'll do number of languages at the bottom, and we'll do our probability over on the left. So for probabilities, the highest probability we go up to is 0.6. So I'll go a little bit past that and go 0.7, 0.6, 0.5, 0.4, 3, 2, and 1. Let me get those spaced out a little bit better. So here would be 1, 2, 3, 4, 5, 6, and then 7. Okay, and then for number of languages, we've got 1, 2, 3, 4, and 5. So at 1, we have a height of 0.63, so a little bit past 0.6, something about right there. For 2, 0.295, so just a little bit below 0.3. For 3 languages, 0.065, so a little bit below 1 for that. And then as we get to 4 and 5, we're going to get to even smaller values. For 4, 0.008 is really just a little above 0. And then same with 5, you've got some very low values there. So there's our probability distribution. We now need to describe what we see. Anytime you hear that word describe a distribution, one word should come to mind, really an acronym, which is SOX. So let's use SOX to describe our distribution. So we've got a right skewed distribution because pretty clearly the tail goes to the right. For outliers, really there are none. For the center, we're going to say that that's somewhere between 1 and 2. That looks like where most of the data is. And for the spread, we'll just talk about the range being from 1 to 5. Okay, so for part C, what is the probability that a randomly selected student speaks at least 3 languages? So we want to know what is the probability that that student X is greater than or equal to 3 languages spoken. So if you think about it, that would be the probability that they speak 3 languages, or that they speak 4 languages, or that they speak 5, and we don't need to worry about subtracting anything off because you either speak 3 languages, or you speak 4, or you speak 5. There is no overlap, so these events are disjoint. So what that ends up being is 0.065 plus 0.008 plus 0.002, which when you add all those together ends up being 0.075. Next, let's find the probability that they speak more than 3. This is slightly different. Probability that X is greater than 3. Now we're not going to include 3. So this is just that they speak 4 languages or that they speak 5 languages. Which probability that they speak 4 is 0.008. That they speak 5 is 0.002. And when we add those together, that ends up being 0.010, so only about a 1% chance that they speak more than 3 languages. Now, one of the big things that we're going to be talking about are the mean and standard deviation for discrete random variables. Let's start by talking about the mean. So the mean, or the expected value of a discrete random variable, is written in this way. So we say that the mean of X, using this Greek letter for mu, so this right here is the Greek letter for mu. In fact, it's lowercase mu. So the mean of X, which is also the expected value of X, so where it says E parentheses X parentheses, that's read as the expected value of X. And the way we calculate it is we take the sum of the values multiplied by their probabilities. And we'll see an example of this in just a moment. In other words, you're taking your first value multiplied by its probability plus the second value multiplied by its probability, and so on until you run out of values. And again, we'll do an example, and it'll probably make more sense when we do that example. As far as interpreting the mean, here's how we're going to do that. We're going to say that in repeated sampling, we expect the average number of blank to be about blank. And that's where you just have to fill in those 2 blanks, and you'll be able to interpret the mean without any problem. So let's do this. For an example, let's go ahead and calculate and interpret the mean for our random variable X in the languages example that we were just talking about. So in order to calculate that, for our mean of X, which again is the same as the expected value of X, we're taking each of the values, and what I mean by values is the number of languages multiplied by its probability. In other words, for the first one, we're going to take 1 multiplied by 0.630. And then we're going to add to that the next one. So we're going to take, for the next one, 2 multiplied by 0.295. Same thing for the next one. We're going to take 3 multiplied by its probability of 0.065, and so on. So the next one, I'm not going to go back up, but 4 multiplied by 0.008. And then the last one, 5 multiplied by 0.002. And if we put all those into our calculator, it should add up to be 1.457. So we would expect about 1.457 languages to be spoken, which should also agree with what we wrote right here for our center. We said the center was going to be somewhere between 1 and 2, and in fact, the mean was between 1 and 2. It's actually almost halfway in between. So now let's go ahead and do our interpretation of that. So we would say that in repeated sampling, we expect that the average number of, and we'll put in our variables, so number of languages spoken to be about, and now we'll fill in our number, so to be about 1.457 languages. Okay, let's take a look at another example. In fact, we're going to be using this example frequently. So we're going to talk a little bit about a game that you can play at a casino called roulette. So one wager that players can make, so one bet that they can make in roulette is called a corner bet. To make this bet, a player places his chips on the intersection of 4 numbered squares on the roulette table. In other words, for those that are maybe unfamiliar with roulette, you essentially put your chips onto whatever spot on the table you'd like. The wheel then spins around and the ball lands in a numbered and colored spot. So you can make a whole bunch of different bets. For example, you could put your chips on even, or you could put them on black, on a number between 19 to 36, a number by itself, just 0, lots of different numbers that you can bet on. The one kind of bet that we are talking about in this example, however, is that we are going to talk about what's called a corner bet. In a corner bet, you place your chips on the corner of 4 different numbers. Rather than just picking one number, you're actually betting on 4 of them. And you can do that in a number of different places as long as it's on 4 different numbers. Now, if any one of those numbers comes up on the wheel and the player bet $1, then the player gets his $1 back plus $8 more, which is great. You know, you've won $8. Otherwise, the casino keeps the $1 bet. So obviously you lose your money if it doesn't come up as one of those numbers. So we're going to let X be the net gain from a single $1 bet. So your outcomes are either that you're going to lose $1, so X is equal to -1, or you're going to win $8, so X would be equal to 8. So here's the probability distribution. Obviously values, you're either losing $1 or winning 8. And probabilities, there are 38 numbers in total, so you have 34 out of 38 chance of losing and a 4 out of 38 chance of winning. So if a player were to make this $1 bet again and again and again, what would be the player's average gain? In other words, what would be their expected value or the mean of this random variable? Well, let's go ahead and find that. So we're going to take our value, so our first one is -1, multiplied by its probability, which is 34 out of 38. Plus the next one, which is 8, multiplied by its probability, which is 4 out of 38. Now at this point, if you just want to put it into a calculator, that's fine. I'm going to go ahead and simplify with the fractions first. So that would be -34 out of 38 plus 32 out of 38. And you add those together is -2 out of 38. Which I'll go ahead and convert to a decimal at this point, ends up being -0.05. So in other words, you would expect on average, if you were to play this game many, many times, to lose about 5 cents every time you play. Now, are you ever going to actually lose 5 cents playing this game? Well, no, you're either going to lose $1 or you're going to win $8. But in the long run, if you look at your winnings over the course of the whole time that you're betting, then on average, you probably lost about 5 cents every time you play. So, does the expected value of a random variable have to be one of the possible values? The answer there is pretty clearly no. Obviously, losing 5 cents was not one of these two outcomes, and going back 1.457 languages was not one of these possible outcomes up here. So then, should we ever round expected values? If they're not going to be whole numbers, should we round them? The answer there is definitely not. And here's the reason why. If we rounded, negative 0.05 rounded would be 0. In other words, rather than saying that on average you were losing, then on average you actually were breaking even. And so this is misleading. If you told me that we were going to break even, then hey, I might play the game because at the very worst, I walk out and I'm still the same as when I went in. But if you tell me I'm going to lose 5 cents every time I play, then I'm probably not going to play that game over and over. So that being said, that is it for this first video, guys. Until next time, have a great day.